Oh, hello. What I'd like to do is I'd like to make up something to you. I'd like to show that for integers, k equals 5 or greater, that 2 to the k is greater than or equal to k squared. And I'd like to do that without calculus. So let's get going here. And so let's just start off with what we want to ultimately show. We want to show that for k greater than or equal to 5 and an integer, that 2 to the k is greater than k squared. Now, before I do this, I'd like to do a preliminary result. So preliminary result. And the preliminary result will be that for k greater than or equal to 3 integer, that 2 to the k is greater than 2 to the k plus 1. And again, I want to do this without calculus. Now, with calculus, it's actually pretty straightforward. Uh, if you take what you do is you can plug in 3, and then notice that it's true for k equals 3. And then all you do is you look at the derivative of both sides, and it's easy to see that the left-hand side derivative will be greater than 2 pretty quickly. Right-hand derivative stays stuck at 2. But we're going to pretend we don't know calculus, so let's do this result first. So let's start off by an induction proof and do the anchor step for a mathematical induction. So if we plug in k equal 3, 2 cubed is 8. 2 times 3 plus 1 is 7. So the result is true. So for the preliminary result, we have truth already. I mean, for the anchor step. Now the induction step, assume true for, I should say, up to. So let's just, I misspoke here. For up for integers from 3 to n for some m. That's the inductive step. And 3, now let's look at 2n plus 1 versus 2 to the n plus 1 plus 1. And this is going to be a simple algebraic argument. So let's start off with this. So notice 2n plus 1 plus 1 by algebra is 2n plus 2 plus 1, which is, of course, 2n plus 1 plus 2. And by the inductive hypothesis, and that's this assumption here, and I actually should have written it down. This inductive hypothesis means for up to n that 2n is greater than 2n plus 1 up to some n. This is the 2n plus 1 that's in this inductive hypothesis here. So we can assume that this 2n plus 2 is less than or equal to 2 to the n plus 2, because this 2 to the n is bigger than this right here. In fact, I shouldn't have equal to, I should just say strictly greater than. But then we're kind of ready to roll. But n is greater than or equal to 3. So 2 to the n is greater than 2 for that. So this part right here, and let's just remember where this came from, 2 to the n plus 1 is less than 2 to the n plus 2 less than 2 to the n plus 2 to the n, because 2 to the n is bigger than 2. This is, so we get 2 to the n plus 1 is less than 2 times 2 to the n, which is 2 to the n plus 1. And that is what we set out to show. So what we've shown this preliminary result right here. So this thing right here, this here has been proved. So now we're going to use that. So now let's go to our intended result. So back to our intended result. That is 2 to the k is greater than k squared for k greater than or equal to 5, integer. So anchor step. Well, 2 to the 5 is 32, and 5 squared is 25. So the anchor step is true. 2, assume true up to some n. That is, 2 to the n is greater than n squared. So now let's examine and let's look at n plus 1. So if I take this n squared, if I take this part and square it, that's this side here, that is n squared plus 2n plus 1. And by algebra, this is going to be less than, see this n squared, this n squared, I'll put it in red here, this n squared is going to be less than 2 to the n plus 2n plus 1. But then, by our preliminary result here, this one right here, by what's in black, that is going to be less than 2n plus 2n, because this is less than 2 to the n plus 1. So we get n plus 1 squared is less than 2n plus 2n, which is equal to 2 times 2 to the n, which is 2 to the n plus 1. So we've proved what we needed to show. Well, so we've shown that. So it means if you want to get back to this sort of the root of mathematical induction, it means that the first false positive statement, for first false statement, it cannot be of the form n plus 1. So this means that 2 to the k is greater than k squared for k greater than or equal to 5, as required. That is a mathematical induction proof. I do want to point something out, though. So the purpose of the video is done, but when I said to do this in class, I got a little bit lazy. If you had some calculus, notice this. Notice that if we instead of n, we look at x and we look at x squared, and we set, let's say, x equal to 5, well, then certainly 2 to the 5 is greater than 25 because this is 32. Okay, so that's not a problem. And then the next thing you notice is that, so if you're comparing functions, this function is bigger than this function for x equal 5. Then if you took a look at the derivative to see the rates of change, what you have, if you took the derivative of 2 to the x, you get log 2 times 2 to the x. Now keep in mind log 2 is what, 1.69 or something? I know it's 0.69 and something. It's a little bit less than 2 to the x. On the other hand, the derivative of x squared is 2x. And what we see right here is that this 2 to the x times log 2, and let's say if you, what you can do is you could see that x equal 5, it's 32 times 0.69 something. That's going to be bigger than 10. Okay. So this derivative is bigger than this. So what you notice is that this function is higher than this, and it has a larger derivative. Therefore, this function has to be greater than this one the rest of the way. You could have proven this by, if you want to be rigorous, you can use the mean value theorem and look at the function g of x equal to x minus x squared. Notice that g of 5 is positive. And suppose there's some g of a equal to 0. So we start 5 here. Here's your function g. Now suppose it happened to equal 0. Then the mean value theorem implies that g prime of some c has to be negative. But if you take a look at g prime, you get log of 2 times 2 to the x minus 2x. I claim that's not negative. If you don't believe it, look at g double prime. And that's log 2 squared times 2 to the x minus 2. This is going to be bigger for x greater or equal 5. Therefore, this is positive at 5 and increasing. Therefore, this is always positive. So the calculus proof that this function is bigger than this one is not bad at all. You don't really need induction, but the point of doing this is to do it without calculus. So thanks for watching.